Having accurate software, mainly FDTD, to be able to close that gap, to have accurate simulations is paramount for us as we kind of mature as a company. We have to do the work. And I think it really starts on the software side, and it also starts on the hardware side. How do we handle sort of our energy infrastructure? Very large problem, very complicated, and it's very difficult for any one person to be able to do that. You know, the software that Flexcompute offers is going to be very key to closing the gap between design and sort of reality.
All right, Steven, it's really good to be here with you at headquarters. If you can, just introduce yourself to us and tell us a little bit about yourself and your background.
Sure. Well, I'm Steven Estrella. I'm the Director of Business Development here at Quintessent. Joined about almost a year ago. I've been in the photonics community now for almost 2 decades. But I've grown up here locally, went to UCSB just across the road here, did my undergraduate work and my graduate work in electrical engineering, but specifically photonics. And it's been an exciting ride from being an engineer and now kind of going to the dark side of doing sort of business development. But it's very enjoyable work.
Everywhere you go these days, you hear everybody talking about AI and the large-scale computing to support that. But at system level, there are some bottlenecks that are sort of hidden, right, that not most people know about. Can you talk to us about what those are?
Sure. So right now, it's no longer really compute that's kind of the bottleneck for these large-scale systems. It's now actually communication. So the ability to speak between these sort of large compute nodes. And it's really driven by multiple factors. So there is the need for very large-scale models for AI. There are some limitations with these individual chips themselves. And so really the problem has been, how do we build up networks that are large enough by putting a lot of these chips together to be able to address these very complicated problems? So it's really more of a network problem now to be able to have all these kind of chips together. And so it's really about making connections and pathways that have enough bandwidth to enable these GPUs to talk to each other so that eventually we can realize all the great benefits for AI.
There's a lot of money that's been spent on compute, right, for these data centers, not as much on the communication pathways, as you mentioned. Do you see a shift, and sort of how do you account for that, and how do you think about the change and the transition to addressing communications?
Yeah, well, I guess backing up a little bit, so yeah, there's obviously been a real nice march over the past, let's say, 50 years for developing sort of the microelectronics, right? We've been following this Moore's law for shrinking sort of the node size and really increasing the density for these chips. The chips themselves have even grown in size, and now people are even making sort of wafer scale devices. But really, to practically do this, the challenge is making, you know, decent sized chips, and then how do we connect them? And so right now, there's a big problem within the industry of how to close that gap. So there have been lots of investments made, obviously, sort of on the chip side. We're seeing a lot of that happening now. And the industry is now realizing we need to play catch up. And so the catch up is really in the communication mechanism, or the interconnect. And so I'm hopeful, and we are here as well, that there is going to be a real surge in development for those components, not only in the commercial sector, but actually even at the government level as well.
What was the inspiration for starting Quintessent, and what does Quintessent do?
So again, if you look at sort of what are the problems, right? I mentioned one of them, which is how you kind of communicate between them. That's definitely one of the biggest ones. The other is the fact that these data centers, they consume a lot of power. And a lot of the power goes to cooling these chips, and a lot of power actually goes to the communication pathways themselves. Another problem is sort of the reliability of all of these mechanisms working together. For applications like AI training, these are like multi-day operations. And so if any one component goes down, well, that's no good, because then they have to start all over again, which is quite costly. So we looked at this problem set and realized, well, the best way to solve the interconnect problem is to do this optically. There's a lot of bandwidth that can be utilized there, but it has to be done in such a way that it provides a low-cost pathway to do this because of the scale it's required to be done. And it has to be extremely reliable. So the technology that we utilize is these are 3-5 semiconductor quantum dots that are married or bonded to a silicon-photonic platform to be able to realize on-chip sort of lasers and amplifiers, which hadn't been done really previously at scale before. And this is going to enable new optical interconnect architectures. Again, as I mentioned earlier, this technology was kind of spun out of the university, so it was a kind of a nice marriage of transitioning research sort of into the commercial sector to address a very real problem today.
You've talked about it a little bit. What makes Quintessent unique, and what benefits are your customers realizing?
So there's a few benefits and things that make us unique here. So one of them is the fact that we're using fundamental materials, these are quantum dots, that are actually providing very high reliability. This is extremely important because there are going to be so many of these devices that are going to be out there in the field, and so the uptime is really important. So starting with kind of foundational materials. The second piece is that this is done on sort of a CMOS platform. So we're leveraging sort of that ecosystem and then eventually the economies of scale to be able to offer sort of lower cost solutions. And so the main use case for this is actually going to be in a scenario where it's going to be a laser source that's actually going to be kind of outside, away from where all of these kind of compute structures are. But because of the way that we implement it and the materials are involved, there's actually a direct pathway to be able to bring that right back in and be able to have it on chip, which is really unique and advantageous, and not many people are able to do that. So those are kind of some of the differentiators for us. But this does have real results and benefits for our customers. So one of them is that we'll be able to offer about 100x increase in reliability. This is very important. In terms of energy efficiency, I mentioned that's another big problem. We're able to offer about a 40% decrease in energy for these optical interconnects. In terms of bandwidth, this is really a light source, so this is kind of one piece of the puzzle.
Yeah.
But because of the nature of that laser and the multiple colors that we're able to generate from that, we're able to offer up to about an 8x increase sort of in bandwidth there, but very much dependent on the system architecture. And then lastly, looking kind of a lot further out, when all of these kind of components come together, we're estimating that this will be about a 40% cost savings, because you get to strip away a lot of the packaging and other pieces that kind of go around that make it quite expensive.
Yeah. At Flexcompute, we're thrilled to partner with Quintessent. Can you talk to us a little bit about why you selected Flexcompute and chose to work with us?
The type of devices that we need to make, these are mainly lasers. And they are quite challenging. And there are many features that are involved to make these happen. And so the ability to do accurate and fast simulations is paramount for us. Our customer needs are evolving, and therefore our designs evolve, and we need to be able to react very quickly to do that. So we were using some other software sort of before, but we really like sort of the FDTD model that Flexcompute provides, or at least the algorithm and ability there. Yeah. And our team has heavily utilized that product to be able to do very accurate sort of simulations, to be able to corroborate sort of measured data with sort of simulations, and it enables us to really kind of close that loop between here is the design, sort of here is the fabricated device, and where do we go from there?
Everybody talks about this desire to innovate. What has this enabled you as a company to do in terms of innovation? So we operate at kind of different scales, right? So one of them I mentioned is sort of lasers, and the feature scales there maybe are sort of sub-micron. But really at the end of the day, we're making photonic integrated circuits. So this is a whole nother level or scale of devices. These are on the order of about millimeters. And to be able to connect simulation from that small scale to this large scale, that's like 3 orders of magnitude there. So we're really utilizing the software to go from sort of multiple scales, from sort of the sub-micron level all the way up to sort of the millimeter scale. And having accurate software, mainly FDTD, to be able to close that gap, to have accurate simulations, is paramount for us as we kind of mature as a company and realize more complicated photonic integrated circuits. What about the people side of things? One of the things that sometimes is forgotten is what does this do for engineers? What are your engineers saying? What are they now able to do, and how do they feel about being able to leverage a platform like Tidy3D from Flexcompute?
So we have many users within the company who use Tidy3D, and so they are able to go off and really do sort of a design of experiment and really dream up sort of what would be sort of the ideal case for us, and then to be able to compensate for maybe some fabrication tolerances, And so having access to, it's really the GPU-accelerated product, FDTD, that's really been leveraged by our engineering team and really enables them to go off individually and kind of focus on a particular area or device, but then really to be able to bring all those simulation models back together again to be able to do more kind of coherent circuit level sort of simulations. So it's really a nice sort of divide and conquer, and people can choose to access it through sort of the GUI that's available, I think through PhotonForge, but also through the Python interface, which our company uses quite a bit.
You mentioned PhotonForge, our circuit level layout and simulation platform, and how that works with Tidy3D. Can you talk a little bit about your growth plans and what this is going to mean for your team? How big is your team now, and what are your projections in terms of growth from an engineering perspective?
So right now we're about 20 people, mainly a lot of engineers. And right now we're very laser focused on kind of making this initial product, which is kind of more of a singular device. But we have plans in our roadmap to be able to expand that sort of even further. And as I mentioned, these will be more integrated circuit level type products. So we're starting kind of small, and the tool is being well utilized, I think. And as we continue to grow and bring on sort of more engineering team, I think it's very clear that the needs will only grow from there. And so I'm fairly confident that FDTD will play a critical role there.
Let's take a look into the future now. So what do you see, or where do you see Quintessent in the future, and what role do you see Flexcompute and the platform PhotonForge and Tidy3D in that journey for you?
So, our vision really is to enable very high bandwidth within the data center for AI applications. We're doing this by enabling kind of multiple wavelengths of light to be able to communicate with. And so the real heart of this problem is sort of addressing the laser kind of first. But as I mentioned in the very beginning, this is really a networking problem at the end of the day. And the use of multiple colors in a network is actually not a new concept. This has actually been around for a number of decades in telecommunications industry. This is known as dense wavelength division multiplexing. So we're bringing that technology really inside of the data center to be able to enable just higher bandwidth. But once you can enable multiple wavelengths of light, and to do so at a high reliability and kind of low cost, it does kind of pose the question, what else is sort of next? What else can we do? Yeah. So there's a lot of kind of thinking kind of going on in the industry. I think something like optical circuit switching might be stand to benefit from this type of technology. But we have sort of visions for kind of more complicated devices, ways to interconnect a lot of these compute resources together. And I think it's safe to say that the community, not just us, has a real need to be able to simulate these devices. And so, the software that Flexcompute offers is going to be very key to closing the gap between design and sort of reality.
So obviously we're talking about a lot here, Steven. We're talking about AI, we're talking about large-scale computing and communication bottleneck. What does it mean to sort of the average person on the street? Sort of how do you talk to them about that so that they can grasp and understand, what it is that we're talking about here, and what it means to marry Flexcompute and Quintessent together?
So I spent quite a bit of time kind of talking about sort of the hardware and sort of the innards of like how the AI models are kind of put together, how these different chips sort of communicate to each other. But there are very real applications for using AI, right? We're already seeing kind of some of that today with like ChatGPT. We're able to kind of query it. It's kind of more of an assistant, I would say, kind of at the moment. But I think there is a real opportunity to solve some major problems, right? So for one, like how do we handle sort of our energy infrastructure? Very large problem, very complicated, and it's very difficult for any one person to be able to do that. So I think that would be sort of fantastic. Another sort of use case would be like for autonomous driving. So no one likes to sit in traffic. And so if there are ways to kind of solve those kind of congestion problems, I think AI is well posed to be able to address some of those. There are others sort of within health and medicine. So discovering new materials, new vaccines, new medicines, I think we could all stand to benefit from that to be healthier sort of as a population, as a humanity. Yeah. So I think there are a lot of rich applications that have yet to be realized, but there is no shortage of work that has to be done to get there. I think we are still a few years away from doing it. And so how do we get from where we are here today to then? Well, we have to do the work. And I think it really starts on the software side, and it also starts on the hardware side. And so that means we really need to have large advancements in all of these components and hardware pieces together. And the software that's used to simulate this is a key piece of that. And being able to communicate with light, we believe, is kind of going to be the way it's going to be done. The backbone of the internet is all done through optical fiber communication. So when you query your phone how to get from point A to point B, that traffic is routed through kind of a vast network of data centers, and information is transmitted actually over light. And so the question is, how do you generate that light? And so that's really the key piece that Quintessent is focused on, is really generating that light in a very efficient manner to be able to have lots of information basically going through an optical fiber sort of all at once. And once you are able to do that, there are a lot of things that can be done. We're using a lot of streaming services. Maybe you'll see this through YouTube. That's all being routed through data centers, all being done, all being communicated actually over light. So it's actually, maybe it's a new technology to some of you, but it's actually been around for a number of decades. The challenge now is just being able to do this at such a massive scale, and the performance requirements are now much higher than they were before. So there is quite a gap to be able to close. And so new technologies, new approaches are going to be needed. And that's where we at Quintessent believe we can address how you efficiently generate that light to be able to be used for communications.
Last question for you. What advice would you give to a young engineer entering this space, whether it's from the hardware perspective or the software perspective, perhaps a younger version of yourself, right? What sort of advice would you give them? Where would you point them?
So if I speak from my experience where I started from, I think it's very much applicable today. It's quite simple. It's really just to be a sponge. This field is evolving so fast, and the amount of knowledge that one must have to be able to kind of go off and make real contributions, it's a lot. So my advice is really for younger engineers is just really to try to absorb. If there are opportunities presented in front of you, go after it. And specifically, if you're already kind of interested within sort of the photonics field, or you're looking to kind of get into that, I would say, go for it. Like, there is a real need. There is going to be large investments made in this field, and having an educated workforce is going to be paramount. So if you're interested, please continue doing it. We need you.
Steve, it's been a thrill to be here with you and to talk to you and to meet the team. At Flexcompute, we're excited at coming alongside you in this journey, and we're looking forward to everything you're going to accomplish.
Likewise. Thank you.
Thank you.